So Lori and I, we had this crazy idea to talk about all these topics, starting from, you know, does space have properties? Going through general relativity, special relativity, light, matter, spin one half, charge, Maxwell equations, everything. And the reason is because we can't put possibly everything into one, discussion. It's just so much material. And whenever we talk about something, right, people will complain. Like, let's say we talk about general relativity, people will say, well, yeah, fine, that works. But what about special relativity? That doesn't work. So we kind of have to cover the whole thing.
Yeah,
And I did it before with James, but I thought I want to do it with you again because you have other, perspectives and maybe different questions.
yeah.
And you
That
can
was the
interrupt me
idea is that,
anytime.
yeah,
We can have a discussion on some topics.
yeah.
You know.
We'll have a different discussion than you and James had, like,
Exactly. Yeah.
right? And
Yeah.
so it
Yeah.
doesn't hurt. So just so, the audience knows that, Chantel has already presented all this work on at Inductica channel with James Elias. And so I thought it would be a good idea if we did this together as well
Mhm.
and, see what conversations come out of it.
Yeah, exactly. And what questions and some things I got feedback from the other, videos. So I'm trying to prove some of the simulations or some
Mm.
of the explanations because some things I sometimes think it's clear, but maybe it's not, right? There's always a way to improve things.
Yeah.
So first, today we'll just talk about first of all, why even are we doing this? And we'll just about talk about a very small piece. Just, can we talk about properties of space or, some people call it ether. I know people, ether is a dangerous word to use, but whatever you want to call it, right? Space or
It's
ether.
it's a perfectly beautiful word to me. I just gotta put
I
my light.
know, right? But people have
I love
misconceptions
the
about
word,
it.
and
So
it's too bad that, the scientific community has kind of, it's the word that bothers them for some reason.
yeah, yeah. That's why I put
I
quotes
just
and
call
stuff.
it,
And
I
yeah, yeah, yeah.
sometimes I just call it
Exactly.
the
Yeah,
medium.
exactly.
And then
Yeah, yeah. People can
we
choose their
believe it's a
favorite word,
medium.
right? You can call it whatever you like,
Yeah,
even if you call it fabric of space-time,
yeah,
fine. It's okay.
exactly.
So the reason is why do I want to do this even in the first place, which sounds pretty crazy, right? Because I'm an engineer, right? I like to understand how things work down at the deepest level. I'm not satisfied with some magic explanation or just math. I mean, physics is great. We have a lot of math that explains everything, right, from quantum physics to general relativity. But what I see missing is the explanation, like why? Why is the speed of light constant? And what is bending? Why is our clocks ticking more slowly when you move? There's no explanation. It's just given as well. That's just what it is. Shut up and calculate. And I don't like.
Exactly.
I'm just not satisfied with that. I
No.
want to know, like with a car, right? I want to know how does the steering wheel work? And for cars, people would agree it makes sense to understand it, but for some reason, people are satisfied not understanding the
Yeah.
universe, which is to me kind of weird, but maybe it's just me. So I don't know.
That's 100% my motivation. I just want to know. I don't know, like, want to take credit for anything. I'm not trying to prove anything except to myself. I
Yeah,
want to prove it to
exactly.
myself, and
I
I
just
don't care what anyone else
exactly.
thinks.
Mhm.
Yeah.
And my biggest hope going through all this stuff is maybe some people will find this interesting and also start to question more, ask, and start to research and maybe,
Mhm.
not just take everything for granted that we read in books because otherwise science would kind of stop, right? So I think there's, room to move forward and I hope people will get interested in that.
Mhm.
So, and another part, of course, is quantum physics, right? This is like, to me, a big red flag. When you have a theory that has like, I don't know even how many explanations there are, at least nine, I think, or 10. That's weird. Like, we don't have nine explanations of how cars work because that would be strange, right? Like, one group of people claims there's this magical thing inside the car that somehow, I don't know, propels it. Like, that would be so
And
strange.
when you put your foot on the pedal, the car moves forward. Therefore, the pedal is causing the car to move forward.
Yeah, or
Right?
consciousness. It's only conscious people can drive a car. Like, how weird would that be if you would say, you know? So anyway, to me, the fact that there's so many interpretations of quantum physics and each group is convinced theirs is right, right? I've had lots of discussions on some forum, and also what's interesting, actually, these even when you dig into these, they don't really explain anything actually at all. Like, yeah, sure, maybe the pilot wave sort of explains some stuff, but we'll have a whole episode on that.
Yeah.
Even that one doesn't, because even here the wave function is
Still not an
mathematical.
explanation. Yeah.
Not, yeah, yeah, exactly. So I was thinking we should just add a new one. I'm calling it neoclassical, whatever. It's just the mechanical model. I want something
Mhm.
mechanical, like a car,
Yeah.
basically from the ground up explains everything. It has an ontology, and even even if it, let's say, turns out to be wrong, right? At least to me, it helps me understand how everything relates to each other. Maybe in the future, I have no problem being proven wrong. Actually, that's how science
Yeah,
works, right? Um,
exactly. Yeah.
that's fine with me. So what are some of these questions? You know, Here's just some of them, and we'll actually go through all of these in detail. Okay, so space time, right? Supposedly, there's no absolute space at all, right? This is what standard physics says, but it can expand and curve. Well, that to me is kind of a logical problem, right? Well, if there's nothing, what is curving? So, there's no mechanism for general relativity, right? Um, yeah, there's a formula, but there's no explanation. In special relativity, it's just, well, speed of light is constant. That's it. There's no reason why. There's no
Yeah.
explanation.
It's a postulate,
It's a
not an
postulate. Yeah, yeah.
explanation.
Of course, it's a useful. We can do math with it, but I want to understand why. I'm not going to go through the whole table here, but just some
Mhm.
other things maybe, spin one half is this mathematical property, but there's no physical model for it at all. Like the electron has spin one half, but it's not rotating, right? Based on the physics, on the standard model. So what is it that's spinning? Well, it's nothing. It's just mathematical. Like, how can that be, right? So that kind of
It's
bothers me.
all, yeah, just very bizarre. And so,
Yeah.
like, because I work in terms of like the speed of light being the same everywhere, I mean, I work in the field of medical imaging and we deal with
Hmm.
like 3D ultrasound. And so, I spend a lot of time with mediums. Like, we build these agar phantoms literally made out of jello. I know you use the jello analogy a lot, and we make our phantoms out of jello, basically.
Oh, cool.
It,
Hmm.
and so, I've been thinking about this for a long time and looking at these phantoms going, we are trying to match the speed of sound of human tissue
Hmm.
by manipulating this medium to be that speed of sound. Because the
Yeah.
speed of sound is the speed of sound in that medium because that's how we constructed the medium.
Yeah.
So, by saying there's a medium, then you don't have to explain why it's the speed of
Hmm.
a wave in that medium. And so
Exactly. Yeah.
it doesn't have
Hmm.
to be a postulate. It can be in your approach, your mechanical approach, it's the medium that makes that
Exactly. Yeah.
speed of light,
Yeah.
speed of sound, whatever you want to call
And
it.
we'll explain
Exactly.
exactly, like slowly we'll go through, and hopefully this time I can make it so that every step is clear. Because sometimes I may be jumping skip steps, so hopefully not this time. I'll try. And
Yeah.
also, I really have to show this because this is not just my stuff, right? I mean, a lot of this is based from a lot of different people. Like,
Yeah.
Robert Close is probably the main person who kind of started
Yes.
this. He has written books, okay, and many papers. So I'm not going to go into the mathematical details. If anyone wants to know more details, there are papers, there are books. Ilya Schmelzer has papers. Sergei Radkovsky has many papers. Marek Danielewski has papers. Hagen Kleinert. So I'm not going to
Yeah.
repeat all the details. That's because that part is well known, like the math. But I want to
Yeah.
add the explanation to it, right? The ontology.
Exactly.
So
Yeah.
that's why I'm not going to. Otherwise, it will be like another 20 episodes, and I don't want to do that really.
Yeah.
Also, a lot of discussions. People asking critical questions. You also hear, see?
Yeah. I
That helps,
recently
right?
ran into the work of Henry Lindner,
Oh
which I
yeah,
find
yeah,
really
yeah.
fascinating. So,
Hmm.
we could maybe at some point talk about his work. And I know you don't agree with
Yes.
everything, or James doesn't agree with everything he says, but it's an interesting,
Yep,
I like
he's
what
on
he,
here too. Yes,
yeah,
exactly, exactly. So, okay, let's start then. Today, we're not going to talk about the details of general relativity, just the basic concepts of, what's the mainstream view of space-time, and what is
Mhm.
there anything we can derive from that, right? So
Yeah,
basically, this is the modern view of space-time, of course, a little bit simplified, but basically the idea is, and we see this image a lot, right? There's space-time is curved, right? And it's curved by mass. And basically the ontology that we hear is that, well, it's geometry, right? It's basically mathematics and geometry. There's no actual thing. There's no actual material. It's just geometry. And
yeah,
so there's no atoms here. There's no microstructure. There's no true fabric, although people call it fabric of space-time, right?
yes,
And well, general relativity is basically the equations. They tell us how it works, but not, well, they tell us the formulas, but they don't tell us why or any mechanism. So here's basically simplified. It's just, I'm not going to go into the details, but basically one side has, on the equation we have the curvature, how much, the whole thing is curved. And on the other side, we have anything related to mass and energy content. And here I have this. It's just a very simple simulation. Let me just show that real quick. So, we see that basically a lot, right? Where, yeah, mass somehow is able to curve this fabric, and
Whatever it
this
is, yeah.
fabric is telling mass how to move and how light is supposed to move, right? But there's no mechanism. So now I always thought it's good to look at history because people obviously have thought about that, right? Like it's not like we're not the first people to think about this. So,
Yeah.
and since most people respect Einstein, so I thought it was a good idea. So let's see what he said because I know as soon as you get into something like ether, people will call you, oh, you're a crackpot. Well,
Yep. You're
let's
discouraging.
see what Einstein. I think if he said something about this, it should be okay to continue this line of investigation. Seems to me. And he clearly said enlightened, although for some reason, people don't want to accept that, but it is true. He said that. According to the general relativity, space is endowed with physical qualities. So, in this sense, therefore, there exists an ether. So, and literally, this whole series, all these episodes, is really just based on that one question. Once we start saying, well, space has properties or ether, and we figure out what kind of properties these are, from that you can draw conclusions. Well, if that's the case, then you would expect this and so on. And basically we can go through this whole thing just based on that alone. It's literally just that sentence here. And he even said, so according to the general theory of relativity, space without ether is unthinkable. I mean, I think we should take this seriously, right?
Yeah. Well, scientific community puts Einstein on a pedestal,
Mhm.
except when he says this.
I
They don't,
know he
like
must be
they say,
stupid.
why should we should take him seriously?
Yeah.
I know some other things about Einstein actually when we can talk about it some other time, but I read a book by a guy named it's called Before the Big Bang
Mhm.
by Ernest Sternglass. And Ernest Sternglass met Einstein as an undergrad. So he graduated. He had his own theory about what happened before the Big Bang, and a lot of my ideas came from him.
Mhm.
He actually met Einstein, right? He went to his house and was able to describe his theory to Einstein sitting in his backyard in his beautiful garden, he as a young man. And Einstein, as he was leaving, Einstein said, "Do you plan on going to graduate school?" And Sternglass said yes. This was all written in the book. And Einstein said, "Well, I don't." He was discouraging him from going to graduate school. He said, "Get a cobbler's job, get a simple job, so
Mhm.
that you can make your mistakes in private." He said, "Make your mistakes in private because you're always going to be remembered for your mistakes,
Oh,
So make
that's
your
oh
mistakes
wow.
in,
Yeah, yeah. Mhm.
flesh out your theory, make your mistakes, figure it out, then bring it to the public kind of thing." So
Mhm.
he was
Mhm.
discouraging him from, he didn't have good things to say about academia. He said it will crush your curiosity and like basically destroy your
Yeah.
spirit.
But there's a risk that when you go to school, you believe everything the teachers tell you, right? You believe everything that's in the textbooks. And we
Yeah.
know, all through history, books are not perfect. They have mistakes. Teachers are not perfect. But still, students are very, they believe what they teachers say. And it's very hard to change that opinion later. I mean, for the longest time, I was the biggest defender of stand physics because I'm like, of course these people know that, right? Until I started asking questions and I got no answers. And then I figured, well, I'm going to have to find out myself, right? So,
Yes.
yeah.
Yeah.
So,
Anyway, so it's
mhm.
an interesting story.
Yeah,
So,
yeah.
do we take Einstein seriously when he tells Sternglass to, avoid academia? What, can we take him seriously for everything he says, or just when he says, space-time is the fabric of,
Yeah.
curvature?
Well, I'm going to take this seriously. And,
Yes, good.
my opinion was, let's see how far we can take this because maybe we can go to some place and then, oh, now it doesn't work anymore. Oh, there's this experiment. It disproves it. Fine. Totally fine with me. Right. And of
Yeah.
course, and I have to, people will immediately object. I know that, in the comments sometimes, Michelson-Morley experiment. So I think even though this is kind of premature, I'm going to talk about the Michelson-Morley experiment right after because it's been misunderstood. And there's assumptions in there that people I guess maybe it's not stated in the books, or people just copy. They just
They,
sometimes copy what other people say. Oh, Michelson-Morley has disproven the ether. Well, it has proven certain kinds of ether. not
Yes,
the one Einstein
exactly.
is talking about.
Exactly.
And so
Yeah,
we have to,
exactly.
people should be open-minded and see, well, maybe, yeah, they missed something, right? And
Yeah,
instead,
they
people always like,
disproved the wrong model of the ether. They had the wrong model of the ether and they disproved it, which is a
yeah,
good.
exactly. And also, as soon as I'm going to talk about, things about it being elastic and speed of light, people will complain, whoa, 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 speed of light is constant. How can you even say it's not? Well, whoa, whoa. So I just want to say, yes, it's correct that for any observer locally, speed of light is always going to be the same. So I'm not even questioning that. And we can show
Yeah,
how you get to that result. But to get there, you're going to have to be open-minded and talk about different materials having different speeds, but they're based on density and stiffness. And sometimes people are just not even willing to look at that. But I hope people will be able to, for a moment, just forget about that, and we'll come back to this. We'll see. Yes,
yeah.
it is constant, but it doesn't rule out an ether or an absolute space for that matter. So let's just go to the Michelson-Morley experiment. We'll talk about this again when we talk about special relativity. I hope, is this big enough? This seems kind of small.
It does look kind of small.
Yeah, I don't know. Let me see if I can zoom in. Well, I guess I can zoom in a
That's
little
okay. Oh,
bit.
there you go. That's a little better.
Yeah. So let's first just take a look. There's nothing moving. So we have these apparatus, right? And
Yeah.
right now, nothing, it's just stationary. Nothing is happening. And I'm even drawing light as little balls, little photons, right? So here's the source, okay? Let's just follow one. So the light goes through this beam splitter, for instance, and then we have one going up and one to the right. They're the same length, and there's a mirror, and then it comes back. And then we have a detector down here, right? So,
Yep.
and the color just indicates sort of the phase of the wave. So we can basically see if they match when they come
Oh,
back
I
here,
see.
right? They
Yeah,
have the
cool.
same
Yep.
phase, right?
Yep.
And so now the idea was, well, let's say this is not a naive model that they used. Okay, so this is what they thought would happen. So we are starting now to move this whole apparatus to the right. So you can see those little this is the
Yep.
ether wind that's in quotes, right? So we
Ether
move
wind. Yep.
right, we
Yep.
can do it a little more just to make it a little more clear. So now, of course, because in this model, right, the speed of light is relative to the ether. So now it's slowing for us as we're going with this apparatus. It looks slower right now.
Yep.
And so you can also see that when this photon here is going to the right, it's slower, but when it's going to the left, it's a lot faster because it's moving relative to the ether. And
Yep.
going
Oh, I see. Yeah.
sideways, it's the same speed up and down because we're moving to the right, right? So now when you
Yeah.
watch these, oh look, they don't match up anymore, right? These
Yeah.
colored
They,
because
yeah. They're a different color when they get to the
I think
detector.
this one is faster. It doesn't even matter which one is, but at
It's
least
fine.
there's mismatch now. So, and of course, the faster you go, the worse that mismatch is. And down here, I have basically what you didn't see at a detector. There's a shift. There's an interference now because the light waves don't add up anymore at the same place. There's a
Yeah.
little shift. Okay, and so the thought was, well, if there's an ether and Earth is moving, right, and we can change the apparatus this way or that way, or in another way, as we're moving through space with Earth, right, at some point we should see this interference, right? That's the thought. And and it was not a stupid thought, it was a pretty good thought. But the thing is, what
Mhm.
they missed something important. Do you know what they missed?
Oh, the contraction in the
Yes.
direction of motion.
Yes, see, they forgot. So when we are at rest, when we're moving, there's length contraction, see?
Yeah.
And they forgot
There
about
you
that.
go. Yeah.
So when there's length contraction, guess what? And it looks like a conspiracy, but when you do the math, it is not. And it's just, it cancels out, whatever. You end up, it looks, you couldn't detect it basically, because now, even though
Mhm.
this speed is still slow to the right and faster to the left, guess what? They end up exactly at the same time in the same place.
Mhm.
There's no interference.
Right.
Yeah, and they forgot
Yeah.
about that. And the
Yes.
reason probably, I think when they talked about this first ether, they thought that light is moving through like, as a wave through the ether, right? But they
Yeah.
forgot to think that what about the apparatus? I think
What
they
about what?
thought that,
What
they
about?
thought that the apparatus was moving like a solid through the ether. So you
Oh,
have
I see.
the drag and you have this wind, and then so
Hmm.
they didn't consider at that time. The thing is, there was no quantum physics there, right? So now we know matter is described as waves. An electron has a wave equation, a Schrödinger's wave equation, right?
Yep.
All matter is described as waves. So, well, what if matter is also waves,
Right.
right?
And what are the implications of that? Yep.
Because then, like this source here, it's not moving through the ether like a rock through water. It's moving through the ether like a sound also, like a wave, like a sound wave through
Mhm.
water. It's totally
Yep.
different. There's no wind. There's no wind.
Exactly. Yeah.
It would be
Yeah.
the same equations like it's both a
Yeah.
wave.
Yeah.
If that's what I'm saying it is, but
Mhm.
that would make it consistent, right? So we
Yeah.
can basically, with this model, we can disprove any model of the ether where matter is not a wave. It's going through the ether like a rock through
Yeah.
water, so pudding or
Yeah.
something.
Yeah. No,
But
I have some experience with solitons in water. Now, I don't know if
mhm,
you ever been in a canoe or not, right? Where
I
when you
have.
drag the paddle through the water,
Mhm.
you create a soliton.
Oh
Okay.
yeah, right. Yes, yes.
Right? I spend a
Mhm.
lot of time watching solitons well, my husband does the rowing and I watch the solitons he's creating when he rows. And
Oh,
so you have to think
nice.
of it, right? These solitons are moving through the water, but there's no water wind. You know what?
Yeah,
They're moving, they're
exactly.
propagating, they're literally propagating through the water. They're moving through the water, but they're not experiencing water wind. There's no forces. And that's why they can last a long time. These solitons last a freakishly long time.
Yeah,
When you
yeah.
create them, you can see them
Hmm,
like,
hmm.
quite a long time. So I think, that you have to think, I know you think in terms of solitons, and so I thought I would bring that up as,
Hmm.
a good analogy to, against the ether wind idea.
Yeah, exactly. And so now let's take a look first of waves in a solid before we go back to some kind of ether model. So what do we know about the speed of waves? It doesn't have to be solid, but basically anything that it can also be, other materials, but basically we're looking at something that has elasticity. And I'll talk about that
Yeah.
again, why. And the reason why is because if we think there is some kind of ether or if space has properties, well, it's got to be able to support electromagnetic waves. And these are
Mhm.
transverse waves. Of course, I know people will say, well, what about vortices? And we'll talk about that too. Also, we know they're gravitational waves. These are transverse, right? And in
Yeah.
order to have transverse waves, you need to have this shear modulus that's related to elasticity. And
Yeah.
when you look at materials on our planet, those materials that have elasticity are usually, we call them solids, like equipment, but it's rubber or steel or diamond, right? All these
Yeah.
have
Yeah.
a
So,
shear modulus and they have a particular density. And
yes. And that's very important because gases and liquids don't have a shear modulus because they can just float, the particles can just, move around past each other.
yes,
In order to have shearing, you have to have like a binding, right? You have to have a
exactly.
binding
Yes,
energy.
yes. And
Yeah, the
I have
particles
like
need to
three
be bound.
simulations on that because I know people seem to have trouble with that. I have like three simulations to
Yeah.
hopefully get this across this time.
Yep.
And like
Oh,
here's
it's
some
very clear to me, but like I said, I spent a lot of time
you have
thinking about
thought about this before, but not
solids
everyone,
and
right?
jello.
Yeah.
Yeah.
So I was just plotting the different materials like graphene, diamond, steel, titanium, glass, aluminum. On the x-axis, we have the density of these materials, like air is very low density.
Mhm.
Then we have
Yeah.
what is this? Lead is more dense, right? And then we have on the y-axis the stiffness. So air is obviously doesn't really have a stiffness, but I still put it there just because to see the density. Then we have,
Yep.
rubber has a pretty low stiffness, and then we have water. Well, I guess water, ice. Graphene has quite high stiffness, and diamond too, right?
Oh, yeah.
Then we have
Wow.
steel. So, and the thing is, what we can do, we can compute the speed of the transverse wave in a material by looking at the square root of the elastic modulus and divided by the density. It's a really simple formula.
Yep.
Um, and when you compute that, right? So we, we have to deal with the speed of light. So we can look at, well, what kind of properties would space or ether would need to have in order to support that transverse wave speed. You can see this is this line. So you can see, well, either it's got to be really, it can either be low density, really low, like if it has really low density, it could actually be
It's both. It's both.
yeah, we don't know where it is, right? But it could
Super high,
be
it could be a super high stiffness and it seems like it should be both, like a very low
probably,
density,
yeah. The thing is, I
yeah,
hope we can find out one day where on this line it is, but it could basically have, the stiffness of graphene as long as it's really low density. Because sometimes
exactly.
people say, oh, it's got to be so stiff, that's not possible. Well,
Yep.
first of all, it's not going to be an earthly material. This is not atoms. It's not, this
Yeah.
is
It's
more,
not atoms.
who knows? I don't know
Yeah.
what to call it.
Yeah.
We call it
I have an
ether.
idea of what it is, but I'm going to wait until after you're done your talk and then we can come back to
Sure.
this.
Yeah, yeah, yeah,
I
yeah.
don't want
So
to
it might
interrupt your
also
flow.
be, basically really dense and oh no, sorry, it might be really dense, but then it will have needs to really, really high stiffness, right?
Mhm.
So yeah, basically anywhere on this line, this is where we have the speed of light. Yeah.
Yeah.
Um, so, and the other thing that's interesting, I think, it wasn't just Einstein who had that idea. It's actually, and it's not even a full list. There are more people. A lot of people thought about that, that it might have to be elastic, right? Which is, Lord Kelvin actually, Kelvin temperature. He thought universe might be an elastic solid, and he was very much interested in trying to figure out if there's some kind of mechanical model. And he had an interesting thought about charge. We'll talk about charge also later. He
Well,
thought
you
charge,
must be a reincarnation of him then, because he said he'll never rest until he finds a mechanical model
well, maybe he was my great, 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 great grandfather.
or something.
Well, actually, not that
Right.
many. I see 1884. Okay, no, maybe I probably not in that case.
Sorry. I, I'll try not to interrupt you too much with, with
Oh,
funny
that's
things.
totally fine. Maxwell also, well, he had this very mechanical model, and we'll have a demo later on that what he had. But he basically did this whole electromagnetic waves using a mechanical model, and he was assuming an ether, and he got the right answer, right? So it can't be so completely wrong because he came to the same, to the right formulas, right?
Yeah.
Stokes also, he had the idea
Oh,
of an elastic solid ether. He actually thought light were transverse waves, but he didn't understand how materials could move through it. That's the thing, right? That's the thing with the Michelson-Morley. So people had in their mind, sure, yeah, 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 light is a wave, but what about a rock? That's not a wave. They thought, well, how could, if it's a solid, well, you can't move through
mhm.
it, right? They didn't
Exactly.
think that,
Yeah.
the rock might also be composed of waves, but that's the one thing that was missing at that point. If they had that idea, maybe it would have been different. It would be interesting to have like an alternate universe where if history had known this little fact, how would it
Yeah.
have developed?
How would it have proceeded? Where would we be right now, maybe? Yeah.
Yeah. And actually Newton, he probably had the most important thoughts on this because when we talk about general relativity, he also thought the ether might be elastic. And he thought that, light was a wave and then that it would be the result of refraction. So, which is
Hmm.
interesting. And that, I will talk about that later. He
Yeah.
said, if the elastic force of this medium be exceeding great, it may suffice to impel bodies with all that power which we call gravity. So he actually had an idea how general relativity could work.
Hmm.
Even back then, of course, he changed his mind. Like he would also think about light as as particles, but he had the idea, and
Hmm.
it's really really interesting. Of course, there are also other scientists here. I'm not going to talk about all of them, and modern scientists too, right? It's people are picking it up again, and I feel like there's more momentum now. People are more willing to look at this again because we still haven't solved, a lot of the questions, and like general
Yeah.
relativity in quantum physics is still not unified. So maybe it's
Yeah.
it's a good time
I
to look
think
at
we're
this
in a
again.
better position now just because of the internet and like you and I can talk to each other, whereas it would be more
Yeah,
difficult. Yeah, we
exactly.
would have to
Hmm.
write a
Hmm.
paper and that paper would have to get published and then you would read the paper and or you'd have to write a letter and mail it,
Yeah, I mean,
this is
mhm,
speeds the I think this will speed things up quite a bit. Yeah.
exactly. Yeah. So let's just look at that. What Einstein said: space is endowed with physical qualities. So the question is, without knowing anything at all other than that, other than we know there's light, we know there's gravitational waves. The only thing right now we can say, well, it's got to be, quite rigid, obviously, right, to
Mhm.
support the speed of light. And we know there are gravitational waves which are transverse. Also, if you believe in the Big Bang theory, it can expand this fabric of space-time. It can curve. So it just means that's the only thing we need to conclude. Well, it's got to be in some way elastic. Some way it has to be elastic. Um, Now, what I mean with medium, I don't mean, just be clear, I don't mean that this medium is composed of actual atoms, because obviously, if
It can't be. It
no, no, no,
can't be.
it
Yeah.
must be something else, right?
Yeah.
It's not made of, that's the only thing I know for sure. It's not made of atoms. I don't know what to call it, right? We don't have a word for it. So I just really want to be clear because in the simulation, it looks like, oh, I have these springs and I have these, I don't know what it's made of, okay? We might as
Hmm.
well call it something,
Yeah. Yeah.
all I know, it's got to support shear waves in some way.
Yeah.
Um, oh, yeah, yeah, of course. And then the other, complaint is, well, wait a minute. You just talked about, you make it sound like this thing is three-dimensional, right? Isn't it four-dimensional? And we'll talk about that because if you consider time can be an emergent thing, it doesn't have
Mhm.
to be an actual space in a way like dimension. We'll get to that, right? We'll make sure everything is consistent. And also how we move through it will be another episode, right? Matter waves, and all that. So the question, of course, is, well, and a lot of people send me emails on this. They say, "Oh, I have the solution. I know what it looks like. It's
Yeah.
an FCC crystal. Like, yeah, I have some simulations on this. So maybe I don't know. I mean, let's just do
Mhm.
some. It could be something like this. I don't know
What
that,
is that? Is that a diamond shape? Or what is that?
no, this is just some FCC crystal. Yeah. Um, well, and some other people sent me
Okay.
this an email actually saying, well, no, I know it's composed of these two different
Hmm.
structures. It has two materials basically. So let's just do something. Maybe, I don't know.
Yeah. For your
So
purposes, it doesn't matter. You can make a medium out of whatever configuration you want, right?
yeah, yeah, yeah. And also I
Yeah.
wanted to mention, because I have a separate episode on that one. It could also be even some kind of quantum fluid that has vortices. So here I'm just simulating. Imagine this is fluid.
That is so cool. I've
You
never seen
have,
that
and
before.
these green things are, yeah, there's a whole episode on that one. We can also do that one later on.
Neat.
Vortices, these are vortices. And the thing is,
Those are
vortices,
vortices?
yeah, you get this like this vortex sponge, and they are actually elastic. So I don't know if you can see it, but let's see, I can increase turbulence. You can pinch them. See, they're
Oh, I see.
like little balloon
Yeah.
animals. They're elastic. So the thing
That is
is,
really cool.
yeah, that's pretty cool, right? We get again elasticity, right? We get the same thing again. It doesn't have to be a solid, but to me, what I just very often, because I don't want to make any claims about the
Mhm.
structure,
Yeah.
right? Um, I do like to have just, let's see, do I actually have any waves here? I think I do. I like to visualize it either as some kind of jello, because there you can't see the
Mhm.
details, right? I just don't
That,
know
how
what
did
the.
you get it such high resolution? That's really neat. Like, make it look more solid without I guess that's super high resolution, right? Or how did
Yeah, yeah,
how
it's
did you
yeah.
do that? I want to know.
Yeah, yeah, I can share. Yeah, yeah, you can
I'll
have
have
all
to
the
look at your code.
simulations.
I'll look at your code.
And
But
also,
that's
so a lot
very,
of
I love it.
simulations, I
It's
might use, sometimes I use this visual, sometimes I use this visual.
Yep,
It doesn't
yeah.
mean I'm
It doesn't
claiming
matter.
anything, because see, the
Yeah.
thing is,
Okay.
what's really, really, really important is what scales are we talking about, right? So imagine this whole galaxy, Milky Way galaxy, the whole galaxy is one electron. Well, Compton, say the Compton
Yep.
radius, right? So
Yep.
that's approximate size. The question is, well, how large is the Planck length, right?
Mhm.
Because that's the smallest thing we know. Well, that's actually a grain of sand. So we know, if the medium has some kind of structure, right? If it's an
Mhm.
FCC crystal, who knows? Then,
Yeah.
well, it's got to be really small. It's got to be order of Planck length. It can't be much
Mhm.
larger than that, because otherwise we would notice, right? It would have to be this size. Well, when I'm simulating an electron, imagine you're writing a simulation for an electron. Are you going to simulate grains of sands on some point?
No.
No. Even
No.
even individual solar systems might be already too much. So, and I don't think we can probe. I think what we can probe is about the size of our solar system, right? With the best instruments we have today, we can't get even near that level of detail. So even if someone would say, tells me, hey, I have this idea, I'm like, well, maybe, but how do I know, right? There's no experiment.
Even from our scale, the Planck scale is so freakishly small. If that
Yeah.
is the scale of the medium, even from our scale, it's so small. Yeah.
Yeah. There might be future experiments because one thing, if the medium has some granularity, then what you would expect, the speed of the light wave would start to change as the wavelength approaches that grain size. It would actually start to slow down a little bit.
Mm.
So, but the thing is, we can't see these waves are too short. The wavelength is too short. We can't even see them. So what I imagine is we have a far away gamma ray burst that was really
Yeah.
like redshifted like crazy. Then, if we get to that range here, we should see that those light waves with ultra short wavelengths would arrive a little bit later.
Mm.
That would be the indication that there is some kind of granularity. But who knows? Maybe that's the smallest thing we see. Maybe the granularity is another 10 orders of magnitude down there. I don't know. So
Mm-hmm.
so I'm not going to make any claims to that at all. Right? I'm not going to speculate. There's no point because as long as we can describe the wave motion using a little bit of abstraction. So I don't need the individual grains to describe a wave. I can use things like the elasticity, the stiffness, the density, right? And maybe I can say something about linearity, like, yeah, it's got to be linear to a certain extent. That's enough. So that's kind of an abstraction that's really helpful in math, that we don't have to always go down to the last tiny little bit. Like when we simulate sound waves, we don't simulate each air molecule, right? We can abstract it a little bit, or water, but there's some level of abstraction. I think that's okay because we can. It doesn't matter, even if you change the underlying details, you'll still get the same equation afterwards, right? So, and I think a lot of people had issues with elasticity. So I'm going to make some examples. Hopefully, first one-dimensional, what that means. So elasticity just means, and this is just one linear thing, right? And I'll have another one in 3D after. It just means when I pull here, there's a restoring force. You can imagine it like springs trying to pull it back, right? That's all it is. You have a restoring force. You can always simulate elasticity using springs and using little attached spheres. So if you have something else, let's say you have a soft gel instead, then you still have elasticity, but then it's just very, it's just floppy, right? It's kind of so you're not going to get the speed of light out of this because it's too floppy. It's got to be really stiff to support a speed of light. And then of course, like some people might say, well, maybe it's some kind of fluid that has some elasticity. Well, the thing is, once it breaks, right? When you have something that can break, then that's it. Your wave would stop, right? So, and because we know light waves, they can travel for billions of years undisturbed. So it's got to be pretty robust. I mean, I don't know if it's perfect. Maybe there's a breaking point. That's quite possible. I don't know. All I can say, at least for some type of waves, like the waves we look at, it is very, very stable. It's very elastic. It doesn't just break.
I just want to point out, you wrote all these simulations, right?
Yes.
These are amazing. Sorry, I'm always impressed when I see like you have a new simulation every time I'm like, oh, I love that. That's so great. It's a lot of work. I know it's a lot of work, but I know you're leveraging ChatGPT, but it's still a lot of work.
Yeah,
So,
it definitely helped me. Like, for instance, I can easily tell the AI, oh, make the surface look nicer or add some controls because that takes a lot of the, the work
that's what
away.
takes tweaking it a little bit here and there, and it can.
Oh, yeah.
And
And also it
it
doesn't have to be
probably
perfect.
knows
It
it
doesn't have to
knows
be.
you by now. So
It knows. And also these are really small things. It's like, 1,000 lines. It's not very big. So
yeah.
Otherwise, you have to be careful with AI. And I want to say this because people keep sending me emails every day about their theory of everything. Literally almost every day I get one. They're all different. Usually they're all written with AI. And it's just sad because there may be some good ideas in there, but you can tell the AI, you have to check it. You can't just believe everything the AI tells you. It will always sound good, but it always makes mistakes. It's just people should really be more careful, not just.
And for this kind of thing, it's very good because you know what you want. You know how you want the software to work. And if it doesn't work the way you want it to work, you'll just tell it
Yeah. It's just to
working.
simulate. Like here, I'm mainly doing visualizations, right? So that it doesn't have to be perfect to the last decimal point because I want to show, like, for instance, here I have, this is one of my favorite ones because it shows different kind of waves you can have in an elastic medium, whether that's an elastic solid or some other kind of elastic. So these are just this one is a simple transverse wave, right? Just the thing you would see up and down. And then notice this one guy, he was on demystify side. He they were talking about me actually. And they're saying, no, that's not possible. You need a surface for a wave like this. You can't have.
No,
No, no, no.
no.
Because the thing is, of course, normally we show transfer waves like this, but they're actually also, let's see, where is it? Linear twist. You can actually have a wave like this also.
Yeah,
You
yeah.
don't need the whole, so that he was worried that
No.
when you have
I
a
think they're
transverse
talking
wave.
about interface waves. So I think they're thinking about interface waves where you have like where the you have the wind and you have the water and the wind blows and it causes the circulation of the water and then you get a wave. I think that maybe when they say you need a surface, I think they're thinking about in like the surface of the water where you need an interface. I think they're talking about interface waves, and this is not. This is in the bulk of the medium, right?
Yeah, and the thing is, so he was worried. I think like when you have a wave going up and down like this, he thought, well, then the whole universe would have to go up and down. You know what I mean? He was
No.
thinking the energy
Yeah.
needed to do that. Well, first of all, we don't know for sure, is it compressible or not? Like it, it's probably. I'm assuming it's almost not compressible, almost not. But I don't know for sure either, right? But if it
Yeah.
even has the slightest bit of compressibility, then it can always have these up and down waves easily. Even if
Yeah.
it's like in this case, I'm modeling, it's absolutely not compressible. Then imagine you can still have these waves. See, in the middle here, it's going up and down,
Yeah.
and up here, it's going sideways. So, but the
Yeah.
surface doesn't change, so it's totally fine. You can have these waves very
Yeah.
easily.
And they're very localized.
They can be localized. Let's see, I have a bunch of other ones. Transverse, longitudinal. Well, longitudinal, I don't know if we have those. For this, you would need compressibility, right? So
Yeah. Because they're springs. Yeah.
Maxwell's equations, they rely only on transverse waves. And then a lot of people say, well, because of that, we have never seen longitudinal waves. There aren't any. Well, I'm saying, are we sure? Because what if there are any and we just haven't detected them? I don't know. I think we
Yeah.
should leave that question open and not just claim because we haven't seen them, there aren't any. Maybe there aren't any, but I don't think we can be certain. So I'm not going to speculate about this, but I'm leaving the question open. So in all the models I work, I'm not using longitudinal waves, but I don't think we should rule it out. And
Yeah.
maybe even think about, well, if there are any, could we detect it somehow? What would it take? I think we should ask those questions.
Yes. I think actually gravitational waves are longitudinal waves in
Oh,
and I talk about that in my one of my papers that I wrote. And I make it sort of analogous to it had to do with the LIGO experiment. And in the light, I make it sort of analogous to an earthquake. So I like to make analogies, right? When you have an
yeah.
earthquake,
Hmm.
you've got the longitudinal wave, which gets there quicker, and
Yeah.
then the transverse wave takes a little bit longer to get
Hmm.
there, right? And so the longitudinal wave, it still creates a little bit, like when you look at the signature of the earthquake, the longitudinal wave has sort of a little fluctuation like this, and then the transverse wave has a big fluctuation like this.
Hmm.
Um, sorry, the transverse wave of the earthquake that
Yes.
causes all the damage is,
Hmm.
it's a, bigger wave when you look at the signature on the whatever the graph is called that they make. Um, and so when they detected the gravitational wave, I looked at the wave and it looked a lot like the longitudinal wave of an earthquake. It looked
Oh, I
very
see what you
similar.
mean. Okay.
And
Mhm.
the idea is, and for the very first one they detected a gamma ray burst shortly after,
Okay.
zero point 0.4 seconds or something like that.
Hmm.
After they detected the gravitational wave, they detected a gamma ray burst.
Okay.
Right? And so gamma ray is a transverse wave. It's a, light
Yeah.
wave, it's a transverse wave. So the gravitational wave could have been the longitudinal component that arrived just a little bit sooner than the transverse wave, which is the gamma ray burst from the two black holes that collided that caused that event.
Oh,
So,
okay. Okay.
right? And so that's just an idea, but gravitate that gave me the thought that maybe gravitational waves are longitudinal and they do travel a little bit faster than light.
Oh, I see what you mean.
Right? Because
Yeah.
they'd arrive first and then the transverse wave will
So
arrive.
I'm using the official model. So here, this is in this model that I have here is it's actually a modeling a gravitational wave, but the
Okay.
transverse, this is at least the model that's published, right? So they use this, it would be this kind of motion. If the wave was
Oh, I see.
what described from the LIGO experiment, it would look like this.
Oh, really? That's really
Yes.
interesting. It's a strange
So from the
motion.
side, you can see, yeah, it is strange, right? So you can
Okay.
see the wave.
Yep.
It's squeezing, like in the middle, it
Yeah.
gets your stuff gets squeezed, and you
Yeah.
get this ellipsoid. I have another simulation right after to
Okay.
with another different
Interesting.
kind of way. Then you also get this kind of
Yeah.
this is another kind of gravitational
Like a
wave.
shearing. Huh.
And I think this one is another one, another visualization of that. So I do have, yeah,
So
this one.
if there
This one
is
is
some compression,
simplified.
then it is longitudinal-ish. It has a longitudinal component, right?
Yeah, I don't know. I mean, it looks like they're saying it's only transverse, but I don't know. The thing is, are we sure? I don't know if we can be sure about that, right? Maybe it's
Right.
just an assumption. I haven't gotten into that great detail. Maybe we should look at this again and read through these papers. What, is it possible that could be a longitudinal component? I don't know. I think what they measured is the transverse part, but I don't know if it's just limitation of the experimental setup, or could we even
Right.
detect longitudinal? I don't know. So here's basically what they're the sort of simplified version of that simulation
Hmm.
here. Yeah. And I think I do have this one. Yeah, that one is fine. So,
Hmm.
um, and also one, this is just one way of simulating it. Like later on, when we talk about electromagnetic waves and so on, I do like the cello view. Of course, you have to
I
imagine
love that.
the
That's
medium
great.
continues all
Yeah.
around, but just to
Yeah.
be able to see that, and I know we haven't talked about electromagnetic waves at all, but you can basically, what I'm thinking is that these waves are also mechanical elastic waves, and actually quite simple. It's just literally waves moving up and down. There's transverse, there's circular waves. Also, this is what it would look like with the
Hmm.
arrows. I'm just drawing the arrows of E and B,
Yeah. That's a like
Um,
a
but
circular polarization.
yeah, exactly, exactly. We can also have optical waves. There are also these optical, let me just remove the arrows here. Optical waves, optical wave modes, which are very interesting. There are also
Hmm.
other kinds of wave shape, but there's so many different possibilities
Yeah.
when you have an elastic medium. Many different
Yeah.
possibilities, right? You can combine them and all that. So
Hmm.
yeah,
Yeah, you can have up down, you can have left right, you can have circular, you can have ellipsoid, you can have sideways, like
yeah,
yeah.
exactly. And of course, people ask, there are some people have gas models and other people, vortices, I love vortices. They're nice, right? The
Yeah.
thing is, and I'll have a whole episode on that. This one here, I mentioned already before, like here we get emergent elasticity. But if you
Hmm.
have a pure vortex model, the one thing I'll say about this, the problem is when you have a fluid and a vortex, these are not waves. You have to use the Navier-Stokes equations.
Yeah.
And the problem is when you have a vortex and then another vortex passing through, they don't. So if you want to model light waves as some kind of vortex, you're going to run into the problem because light beams can cross each other unhindered, right? We know that they're bosons.
Yes, I do. Yeah.
But a vortex, and actually my husband, he did his PhD on computational fluid dynamics. I asked him to be sure. He actually has studied, his PhD work was on finding vortex cores, actually modeling them in water turbines to save energy, whatever, right? He's like, no, that's not possible. Of course not. You can't have two vortices go through each other. It doesn't work. You get these
What
chaotic.
about solitons though? What about
Well,
solitons?
solitons are waves, right? Solitons
Yeah.
are waves.
So, but they're vortex-ish, I guess, but they're not vortex. So,
As long as you model them as actual a wave, it's okay. But when
yeah,
you have a fluid moving
yeah,
around,
yeah,
you have actual particles, they crush into each other. You get
yeah,
turbulences. It's
yeah,
not gonna light waves are not gonna go past through. If you model it that way, you're gonna run into trouble as soon as you try to model a light wave going through another light wave. That's why I think these models. That's why I'm not studying
yeah,
these models more because there are limitations that I saw right away. So I'm spending my time on the model I think has the most chance of actually working.
yeah.
And from all I've read so far, I think something where space or ether is elastic. I mean, it seems to work all the way through, basically, yeah. All
Everything,
the way
everything
these
you've
days
tested
so
so
far.
far,
Of
right?
course, there's still a lot of details, right? So even all these episodes are they're just scratching the surface. There's still questions. What is a proton exactly? What are quarks and why is
Hmm.
charge quantized? there's a lot of questions that I can't answer,
Yeah.
and has to be more research, right? And also maybe there are, like, for some of these aspects, there may be other models. Right now, I have a particular model for charge that seems to work, but if someone tells me there's a different model that works, fine, no problem with me, right? So
Yeah.
yeah,
Exactly.
yeah.
No,
Yeah.
I agree. Yeah.
So I
No,
hope
you've
people can understand like why we're thinking that space has or ether has properties and that it's going to be elastic. And so from now on, we're always going to, keep that going forward, right? Can we
yeah.
explain general relativity with that simple thing? Space is elastic. What about special relativity? What about photons? And so on and so on. And then, yeah, that's pretty
Mhm.
much what I have for today.
Okay. Yeah. So the where I want to try and contribute here is maybe just opening a crack in the door of what the medium might be.
Okay. Hmm.
Okay. So I know like it doesn't matter for your model, it doesn't matter for, it doesn't matter what the configuration of the, medium is necessarily, but I'm very curious and I want to, dig deeper and to try and figure out what it is. And so this is where like so many people that I've sort of studied, and
Hmm.
like Ernest Sternglass that I mentioned to you, who I actually met on the phone one time. Someone gave me his phone number, and I called him about a year or two before he passed away because he was quite old. Um, so his book was Before the Big Bang,
Hmm.
and his model was the universe began as a relativistic electron-positron pair. So
Hmm.
this is where the electron-positron pair idea, this is, one of the first times I started looking at that idea. You had a relativistic like electron-positron pair that were bound together, and that they went through a series, this medium or this thing, whatever, went through a bunch of bifurcations where it split, kind of like cell division,
Hmm.
really, in his model, reminded me of cell division where it split and then it split and then it split. And then after 270 iterations of this splitting, that's where some differentiation started happening. So each pair was the same. And it reminds me of that the Bose-Einstein condensate where you
Hmm.
get one vortex, then you get two, then you get three. Well, his was a splitting process, but it doesn't have to be where, it's something happens and then you get one and then you get two and then you get three, and at a certain point you get a phase transition where matter comes into being, and that's what he perceived as the Big Bang.
Oh, okay.
So, right, and then other people talked about electron-positron pairs. So I'm gonna try and share my
Okay.
screen. Not sure exactly how. I think this will work. Do do do. So how do I? Are you still there?
Yes, I was just coughing, so I
Okay.
turned off the audio for a
I
moment.
don't know. No, I kind of,
I see your PowerPoint, but I see a black slide. Is that on purpose?
yeah, I just set it to black because it was reflecting off my glasses.
Oh,
Um, so you see my screen now and you see
yep.
my
Hmm.
mouse.
Yes.
Okay. So, yeah, so I wrote a paper called The Medium for the Propagation of Light
Hmm.
Revisited, where I started talking, I trying to investigate what this medium might be. Okay. And so the idea is that, everything is waves. So in order
Hmm.
for a wave to form, something must be waving,
Yes.
obviously.
Yes.
And and all waves that propagate require a medium, right? So that
Hmm.
seems obvious to me.
Yeah.
Okay. And so, and then this equation here. So then I go back to the speed of sound because that's something I'm familiar with in my job. And so the speed of sound
Hmm.
is
Hmm.
calculated with, some,
Yeah, it's the same one I showed actually. It's the same formula.
stiffness, stiffness constant.
Yes,
Like
same.
for a
Yeah.
solid, you got to have a stiffness constant and a
Yeah,
density
exactly.
coefficient of
Yes.
some
Hmm.
sort. Okay. And then, but then we also have, this formula here for the speed of
Yes,
light.
exactly. I mean, no
Okay.
space has permittivity and
Yeah.
permeability, right?
Yeah. Yeah.
So, like,
Which are
even if people say,
properties.
"Oh, space doesn't have properties," it does have properties.
Yeah,
So,
exactly. So this is, permeability and permittivity. So, this is how we calculate speed of light, and this
mm,
was, this sort of has some history behind it, but I wanted to write an equation that looked like this.
Hmm.
Okay, where it had, a numerator and a denominator, and the numerator stood for the stiffness coefficient, and the
Yes.
denominator stood for the something to do with, the density of some
Hmm.
sort,
Hmm.
right? And so so you can write it like this. So the speed of light is the square root of the Coulomb constant. Okay, so 1 over 4 pi times permeability is the Coulomb constant
Hmm.
divided by what I'm calling the magnetic constant.
Ah,
So,
okay.
right, the magnetic constant is, permeability divided by 4
Oh,
pi,
I see. Okay, yeah, yeah.
right? So
Hmm.
basically, when I take this formula and multiply it by 4 pi over 4 pi, which
Yes.
then now I can write this formula here, and this looks a lot more like the, formula that, we use to calculate in speed of sound in a medium, in a solid
Mm-hmm.
ultrasound. And so you can think of this. So the Coulomb constant is the inverse of permeability. Now,
Yep.
permittivity, sorry, permittivity permits a, electric field. And so the inverse of permeability or permittivity is does not permit, it's a resistance.
Hmm.
So that, right? So that could be, this gives us the idea that this it would create a stiffness of some sort,
Okay. Hmm.
right? So if it's resisting, electric, field or electric
Hmm.
charge or electric orientation of whatever the medium is, then that's going to create a kind of a stiffness.
Okay.
Right? So there we have a stiffness constant, and the magnetic constant is related to magnetic flux density. So you have kind of a density-like term
Okay. Interesting.
down
Interesting.
here, and you
Yeah.
have kind of a stiffness term, up here. Okay.
Hmm.
And so that's, I just wanted something that looked more familiar to me. And so that's what I wrote about. In my paper, I did it the opposite. I put the magnetic constant. I put permeability on top. So the inverse of permeability is not permeable, which is also a stiffness constant,
Okay.
right? And then permittivity is, kind of becomes more of a density coefficient. So
Mm-hmm.
because of the way they write it here, it can go either way.
Okay.
Still, it's something that's familiar. I can say, okay, this is
Yeah.
a
Yeah. Hmm.
property. This has
Hmm.
properties,
Hmm.
right? And so then the question became, okay, what is the medium? What is it made of?
Yes.
Okay, and so I'm saying the medium is made of electron-positron pairs based on other researchers. Like there's other researchers, a guy named independent researchers you probably never heard of. A guy named David Toom had an electron-positron pair medium. A guy named, let's see if I have this
So
slide
the
here.
question there is, of course, that requires you to have a model of the electron. So
Yeah,
what is an electron, right? What is a positron? So, and
right. If
yeah.
they're, I think they're like solitons, they're waves. They're solitons. But yeah, so then is it so I don't even want to say electron-positron pairs. I want to say vortex anti-vortex pairs, right? To be more in line with this paper that I gave you, this PhD dissertation thesis, right? So this is where I get into the Bose-Einstein condensate. And so I'm saying that the universe began kind of like what Ernest Sternglass talked about in as an ultra cold, instead of starting from a hot dense soup, it starts from a cold dense condensate of some sort. It can't be a Bose-Einstein condensate because that's made of matter. When you take matter and cool it down, you get a
Mhm.
superfluid. And so it can't be that. It has to be something else. And so the idea is that it's made of electron-positron pairs.
So one question I have
But
about
they're,
this, one question, because we know electrons, they can move through double slits, right?
yeah,
That's to me, I'm going to talk about it a little bit later. We have any model that we have of the
yeah,
universe needs to be able to explain how an
yeah,
electron, even a single one
yeah,
can go through both slits, right? At the
yeah.
same time. So how would you explain
Well,
that?
the electrons and positrons are solitons, in which case they're waves. They're
Okay.
not vortexes. They're not vortices in the standard sense. And even in these Bose-Einstein condensates, I'm pretty sure they're thinking of them in terms of solitons and not just vortices, even though they call them
And
vortices.
then what is it of what? Like, or a soliton of what? Then it still asks the question, raises the question, what is it made of? Like, what's the positron electron made of, right? Because you, when you
Right. It
say
would be,
the
yeah.
basic
So
building blocks, then what is the positron made of, or and the electron?
Well, it's
Like,
just it's got opposite angular momentum.
okay.
It's leaning in the opposite way. So this is the picture of the Bose-Einstein condensate
Yes, yes.
forming these vortex pairs, forming these vortices in the bulk of the medium. And so this is where I get into the idea, okay, the black dots, that's the medium, right? Because they are solitons. They are, they spread out in a way. So this could be the elastic medium. This could be an elastic
Okay.
medium
Mm.
because, they kind of there is sort of there is a kind of repulsion, it looks like, in these in this field here. And so it forces them into this triangular shape, which is why I actually model when I recreated your soliton, your spin one half animation. I did it
Mm.
using this hex kind of a grid or triangular grid,
Okay.
just because it looks prettier. I
Mm,
just like
mm,
it,
mm.
but also because I want it to model what we're seeing here. And of course, in 3D, you're going to end up with they're going to be more like tetrahedrons. And they're going to be triangles like in the 3D model I gave you, which was made of triangles. You can make any shape out of triangles, right? So triangles are a nice, way if you want to build up,
Oh yeah, totally. So one question I have
structure.
here, because each dot is really a vortex, right?
Yeah,
It's basically,
yeah,
so it's not like
yes,
it has an elongation. So if we would flip it on the side, we would see these lines going down. So how would you make this? So and actually, what I know is
yes,
that this when you have these vortices, they are actually elastic. So they do, you could
yeah,
shift it. I don't know how to show this, but you can shift it
yeah,
relatively. You can create these waves. They are
yeah,
elastic. The thing
yeah.
is, it's only two-dimensional, like because if
Yes,
you
these
flip
are
it,
these are two-dimensional.
yeah,
So
yeah.
I would have to figure out how that works in 3D, and I don't have that figured out
Yeah,
yet.
this is where
So
this is where I got to the vortex. This is how I got to the vortex sponge,
yeah,
because when you
yeah,
have like in three-dimensional and you have like all these vortices, in a curled
yeah,
up, then they can be elastic. The whole thing can
yeah.
be elastic, basically.
Yes. Oh yeah, okay. So that's it. That might be a nice hybrid of what I'm trying to get at here. Right. And so here, this figure here, I really like because it shows when the pairs, so you got these vortex pairs, and when they're paired, when the vortex and anti-vortices are paired, the phase, they're very coherent.
Hmm.
The phase coherence is very, strong. So it doesn't the field doesn't expand throughout the whole universe. It's very, very localized. But when they go up to a certain temperature and they start getting unpaired vortices. So the unpaired vortices would be like electrons, protons, like ponderable matter, like it would be analogous to ponderable matter, which do extend where their fields can be detected, for a very far distance, right? So this is just an idea. I am not an expert in this field whatsoever, but this is what gave me the idea that it's possible that yeah, the medium. So when electrons and positrons annihilate, they don't just disappear, they fall back into the medium.
Yeah,
They
so
become
at CERN they do
so
this. Actually, Switzerland, you know what? This is actually in Switzerland, pretty close to me. They do these experiments where they, what you can even do, you can have high energy light waves against each other, and you can create a positon electron pair.
yeah,
So you can turn
yeah,
actually matter into light and light into matter. So basically, when
yeah,
you combine them, they turn into light, so
yeah.
into
Yeah,
gamma
yeah.
rays.
So there's a great analogy. I don't think I have. Let me just see. Um, yeah. So this guy, his name was Menahem Simhoni
Mm,
from the Hebrew University of Israel. He came up with this idea. So this is
okay.
again, he is another independent research that I looked at. He was quite old when I ran into him, so he's passed away since. But what he did was he noticed that so if you take a salt crystal,
Hmm.
okay, salt crystal has sodium and chloride, and they're bound together in a crystal. And he noticed that when he shone a light of a certain intensity or a certain frequency onto the sodium chloride crystal, it became cloudy and electrically conducting. So he's using
Mm.
UV light around 8 electron volts. Okay, so we know that. when particles bind together, they lose a little bit of energy. They lose a little bit
Yes.
of mass,
Hmm.
actually. They release that energy into the medium. So let's say sodium chloride is the medium. He
Okay.
shines a light on it. It releases the sodium and the chloride are released, and now they can conduct within the medium. They stay within the context of the medium,
Hmm.
but
Hmm.
now they can conduct within the medium, and the it looks a little cloudy. And when you take the
Okay.
light away, they fall back into the medium, and they
Hmm.
release the whatever the binding energy. So the energy
Yes.
they release is the binding energy
Hmm.
of the sodium and the
Yep.
chloride.
Yeah.
And they do lose a little bit of mass, but it's a tiny bit, right?
Right.
Just
Yes.
like you can barely measure it,
Hmm.
but they know they do. They know that that binding energy is the energy that gets released in the binding process.
Exactly. Yes. Hmm.
So now take this to the extreme. Now, when the electron and positron, when they come together and annihilate, and most of their mass is expelled into the medium, that they don't just disappear, they disappear from our field of view, but I say they're binding into the medium.
Hmm.
They're binding into the medium, and that binding energy, which is a huge amount of energy, gamma rays, right? 512, whatever.
511.
Yeah.
What is tera? I don't know what. Yeah, a
Big,
lot. Yeah.
whatever. It's a large amount of energy considering how small these guys are. It's a large amount of energy, which is so basically all of the mass, or maybe almost all the mass, except for maybe Planck mass or something, gets dumped into the medium as gamma rays.
From what I know,
And
I think
then
it's actually
so that this
all.
would create
Yeah.
a huge stiffness, right? If this is the binding energy, if the binding energy of, like sodium chloride, the salt is a very solid crystal. It's bound very well. I think the speed of sound in sodium chloride is around 3,700 meters per second,
Mm.
right? So it's so you can then diamond is around 12,000, 11,600 or something meters per second. So the binding energy of diamond is much stronger, much higher than sodium chloride. And then the binding energy of the electron-positron pair is so high that that's why the speed of sound is so fast. And plus, then the density of the particles are quite small.
So, okay, in this model, though, then the electron pulsing will still be there because at least
Yeah,
from the experiment that were done, right, it looks like the entire thing is gone. Like it will converge to light, and also you can
yeah.
have two light
But
beams, and
you
it's
can
going.
pull them back out. The virtual
Okay.
electron-positron pairs don't come from nowhere. They come from somewhere. And so you can pull them back out, but you just have to supply that energy again. Just like he supplied the energy, this, guy um, supplied the energy to release the sodium and chloride atoms and let them conduct in the medium. If we supply the energy, the gamma ray energy,
Mm.
can pull electron, like they know that electron positron pairs exist, right? That
Hmm.
they require them in their equations to balance their equations. So they know they exist. And so I say they're not like virtual, they're not like ghosts, right? That they're literally pulling them back out of the medium. So when they annihilate, they fall into the medium. And when you supply a certain amount of energy, you can pull them back out.
What
Now,
about other particles, though, like neutrinos, protons? There are other types of particles. Like with this model, how would you explain? Because there's two different ways to explain this, right?
well,
One
those
way to
particles
explain.
exist outside of the medium. So those are particles that exist that, don't come from the medium. The electron-positron
Mhm.
pairs do come from the medium. All the other particles came in when the Big Bang happened. This phase transition that Ernest Sternglass talked about,
Mhm.
he referred to it or described it as a phase transition of some kind where
Okay.
then matter was born. So like that's not the matter came out of that phase transition for whatever reason that
Oh, I
happened.
see.
Phase
Mhm.
transitions happen. So all the other matter that exists in the universe, protons, atoms and human beings and galaxies, all emerged from that phase transition. But the medium is still there. So the medium that was there before is still there. It's just new things appeared in this phase transition.
Mhm.
So the medium is still there. It's electron-positron pairs. We know that there's virtual electron-positron pairs. They require them. And also one thing they noticed is, let me just see. So yeah, there's the pair production, okay, is very difficult in empty space. So to get the pair production to happen in empty space is very difficult.
Yes.
Because, and the reasoning, and this is, I looked up ChatGPT, of course, the reason is because of conservation of momentum. So energy needs to be conserved, yes, but also there's the additional
Yes.
momentum,
Hmm.
right? And
Hmm.
so that's why they notice pair production is much easier near a particle, near atoms. So in a vacuum, it's very difficult, but when you're near matter, something needs to they use the term momentum sink. Something needs to sink this momentum, and so near a nucleus of an atom, it's much easier to have pair production,
Oh, I didn't know that. Okay, interesting.
right?
Mhm.
And so my prediction was that you should see, like, I kind of think of a black hole as a giant particle. We should be seeing tons of electron-positron pairs um, coming out of the vacuum near a black hole, and it turns out that's true. They see electron-positron annihilation when they look towards the black hole at the center of our galaxy, right?
Yeah.
They see tons of gamma ray bursts, and so
It could
um,
also be, I mean, another explanation could be that because there's just a lot of energy there, a lot of
yeah,
electromagnetic energy, a lot of light waves, a lot of gamma
yeah,
rays. Of course, and then, if you have so many light rays going, at some point they're
yeah,
going to hit each other and you're going to
yeah.
create electron positons, right?
Well, yeah, exactly. So it just would happen easier as you get closer to a black hole, because a black hole can totally sink a whole crap load of momentum, right?
Mm-hmm.
We should be able to see. And so we are seeing clouds of now their interpretation is different than mine because they think, oh, positrons are being created and then they're being annihilated by nearby electrons. But what I'm saying is no, the pair production, so they are being created and annihilated, continuously in this cloud, right?
Hmm.
And creating a cloud like in this region. So basically we're seeing tons of gamma ray bursts in this region, gamma ray photons, light waves coming from this region. And when they see this exact signature, it has to be electron-positron annihilation. So they're saying, oh, positrons are being produced and annihilating with electrons that are nearby. And I'm just saying, well, maybe it's the electron-positron pairs are being pulled out of the vacuum, which is made of electron-positron pairs, and that they're just being created and they're just annihilating right away continuously. And so it's just a different interpretation of what we are. But I already made a prediction saying, oh, if it happens near an atom, nucleus of an atom, and I kind of see, the fractal paradigm that the black hole is kind of a nucleus of a giant atom, that we should see tons of them there.
Hmm.
So this was a prediction I made in my head. I didn't formalize it or anything, but then I went looking for it and went, oh my God,
Oh, okay. Interesting.
it
Hmm.
actually exists. And so, this is just, again, it's just an idea that I'm throwing out there as a possibility of the medium being made of electron-positron pairs. And it also
Yeah.
kind of makes sense. It actually gives E equals MC squared sort of new meaning. Because if you take the equation, let me see if I can get my pen working here.
I think the main difference is how I would label these things um, because you're basically saying that the electron positron, you do think there's some kind of wave, so right, some kind of soliton, or it has
Yeah,
some structure to it,
yeah,
right? The
yeah,
electron has some because it has charge, it has
yeah.
spin,
Hmm.
so this has to be modeled in some way, like as a wave in some fashion, right?
Yeah.
Um, and when it has, for instance, spin one half and plus or minus charge, we call it electron, right? The thing I might probably use different labels just simply because when electron positron do annihilate, it's no longer the same thing really, right? Because it doesn't have the same amount of energy. It doesn't have the same, even if you do think so, you know, uh, it's still there in the sense that, it's the medium is still there, right?
Yeah.
And but it's not going to have, you're not going to have a plus and a minus charge next to each other anymore, right? Because they're annihilated, right?
Well, yeah, they're basically now behaving like this guy here. where the field is very localized, right? So you don't see them, but they're there, right? So
That
this
would
is
mean, though, that there would be some remaining energy that's still there, right? That would be.
I don't know if I would call it energy because it's dumped all of its ponderable energy to the medium,
Mm,
and now it's just left with maybe the angular momentum aspect of it or something like that. So I don't know. Like I haven't really worked
mm,
this out mathematically or anything other than the fact that when you take so basically if we take this formula here, right? So instead of electric constant, magnetic constant, you would have the binding energy and then the density of the electron-positron pair.
mm, mm.
And you do get the speed of light when you do that,
Okay.
right? So it gives kind of new meaning to like the
Mm,
it
mm.
comes from E equals mc squared. So if you go, I don't know if I can do this. I'm going to pick a pen. I can't see. Sorry. I can't see my menu. Oh yeah, draw. Okay, let me pick a pen here. So if you go E equals mc squared, and then you go C squared is equal to E over m, and then you use this as the binding energy, and you use this as the mass density
Hmm.
of, say,
Hmm.
you take the two
Oh, I
particles,
see what you mean. Yeah, yeah.
right?
Okay, yeah.
Then you have the equation that we want for the speed of,
Oh, I see what you mean. Okay.
right?
Mm, mm, mm.
So yeah, and so this could work, it could be proton antiproton pairs, but I don't think it is because we don't pull proton antiproton pairs out of the vacuum. We pull
Yeah, the thing
virtual
is, I guess what I find difficult to understand is that kind of means there's two different models for matter because then you have one model for quarks and protons and neutrinos, and then you have a different model for electrons and positrons, right? So you need, in a
Well,
way.
this is different. This is
Mm,
electron-positron pairs.
mm,
So it's kind of like when you take sodium and chloride and
mm,
you put it together into salt, it's no longer sodium and chloride. It no longer has any of the qualities of sodium and chloride. It has a new quality.
right.
It's right.
Mm,
So, yeah. And so electron-positron pairs, when they are in the medium, when they annihilate and fall back into the medium, the properties are completely different than when they were electrons and when they were
oh,
positrons,
okay. Okay.
right? So they're
Mm,
different, once you pull them out, and then there are excess electrons, like at this phase transition, then so below the phase transition, where there's only electron-positron pairs, it's very symmetrical, it's very coherent, like in this one here. But then when the phase transition happens, then you end up with unpaired. So then you have electrons and you have protons, not positrons, and you have neutrinos
mhm.
and all these different things coming out of the phase transition. Then you've got different behaviors than what you have here.
Yeah.
So this is coherence and this is incoherent. So broke, they call it symmetry breaking. The phase transition breaks the symmetry of the medium before the phase transition. But so
Mm,
before the phase transition, matter didn't exist, light couldn't exist, nothing could exist. And then like no things that we consider things could exist. So this was just the medium, and then at the phase transition. So that's sort of my model. That's the way the line of thinking that I'm investigating, which
okay.
may not be right.
Well, the thing is, how would you ever prove it, right? So basically, what I'm
The-
trying to do, I'm trying to make
I
the
can
fewest
only find
assumptions,
evidence.
you know. Yeah.
It's it's about proving beyond a reasonable doubt. At some point, you can't prove it, prove, but there's a lot of evidence, like the fact that there are virtual electron-positron pairs that physics requires, and that you can pull electron-positron pairs out of nothing. Are we pulling it out of nothing when
Well, it
you,
depends on what you think matter is, right? So if you regard matter as just a wave, some kind of wave in
yeah,
this elastic medium, yeah, of course, it's just a
yeah,
different kind
my
of wave
matter
shape, right?
is a disturbance in this medium. So we
Then you
got the
can pull
medium.
out, then in that way, any wave shape,
Yeah,
what we call a particle is some kind of wave shape, right? So
yeah,
like
yeah,
we are call these transverse waves. There are
yeah,
more complicated wave shapes that have spin waves we call electrons. So
yeah.
in that sense, as long as you have some kind of elastic medium, that has some kind of it's
Yeah.
wobbling in some way, right? So
Yeah. It can
then
be disturbed. It
like
can be
the
disturbed. Yeah.
quantum fluid, whatever the quantum,
Yeah.
sometimes the 0 point energy, right? There's something going on. Then you will always have brief moments where you have this wave and that wave, and you will go, cancel each other again. So
Yeah.
I see it that way. Very simple, actually. Just if there was a beginning of the universe, which I'm not even certain there was, then it's just some medium that has oscillates. It has energy. It
Yeah.
wobbles in some way, and
Yep.
the matter is composed of these different kind of wave shapes. And when, for instance, then an electron and positron annihilate, it's just mirrors. There's basically a mirror image of a wave and an anti-wave,
Yeah.
just like when you have noise canceling headphones. And when even in noise, actually, when you have a noise canceling
Yeah. Yeah.
headphone,
Yeah.
when
Yeah.
the noise cancels, it's not gone. It generates
Exactly.
this heat.
Exactly.
So you get
That's exactly.
electromagnetic waves. So it's just turning one wave shape into another wave shape.
Yeah.
So that's why,
Yeah.
I mean, of course, you could say, well, the medium is composed of these vibrations. I would hesitate to give this a name, because if you call it electron, electron has a certain meaning, like it needs to have charge and spin and mass. So because when you annihilate the positive electron, well, that is gone, right? There's still something
Yeah.
left. There's still some vibration left. And
Yeah.
I think what you're calling it still electron positron pair.
Yeah.
I guess I would
It's
just call it, there's some
well,
waves,
the
there's still
reason I
the
call it
energy is still
that is
there. So
because I want to explain where electrons and positrons go when they annihilate. So that's why I'm calling them,
mm.
right? So I want to have like, where do they go? Did they right now they just disappear according to standard model. They're gone.
Yeah, to me, they're
They're
just labels.
gone.
Like when we detect something, that's when we, like when a light is detected, the detection event is what we call a photon. The wave is still like,
Yeah.
we just can't see the waves, of course. We can
Yeah.
only see it when it interacts with some apparatus, and that's when we call it, oh, this is a light, this is light, and this is a
Mhm.
photon, or this is an
Yeah.
electron. But it's,
Exactly.
when you have a free flying electron, it's also no longer it's not a little ball, right? Because you can actually
Yeah.
create a double slit experiment
Mhm.
with a single electron. You can
Yeah.
split the electron wave, and it will interfere with itself. So this, to me, can only work if the whole concept of electron is actually distributed as a wave. It's not
Yeah. Yeah.
anything,
And the
you know.
anti-wave, so this would be that's we could say wave anti-wave,
Mm,
soliton
yeah.
anti-soliton. Um, vortex is maybe not a good word in the sense
The
that,
thing is, a vortex implies you have kind of fluid, and then you have to do with
yeah,
Navier-Stokes. And Navier-Stokes means,
yeah,
it's the waves don't add up. Like it's in waves,
yeah,
they add up. Like you have bosons,
yeah.
right? So you
You
have
have
a
constructive,
transverse, another.
destructive, yeah.
When you have fluid dynamics, it's a very different thing, right?
Yeah,
It's
no,
different.
exactly. So you don't have like constructive and destructive interference. So
Yeah,
this
exactly
is
right.
kind
Yeah,
of
yeah.
annihilation. If electrons and positrons are waves, which we're modeling them as waves, as solitons as a wave of some sort,
Hmm.
then this would be destructive interference, but that doesn't
Yes.
mean gone.
Well, gone in the sense that the medium is still there,
Yeah,
and there may be some leftover vibrations, but
yeah.
I don't think it's going
Mhm.
to have, you're not going to find, like if you had a microscope, you could look at it. I don't think you would see anything, it would just be the medium itself, because when you disturb
I,
the medium, when you put in energy,
I,
let's say light
yeah,
waves, you could at some point, when you have enough energy, you can create these wave shapes again, right? It's just difficult,
yeah,
of course, because you need the
sure.
right shape and
Yeah,
all. You could create them again, right? So
yeah,
that's how I think you can create with enough energy. That's what they do at
mhm,
CERN. They bombard particles, and then they see what comes out of it, right? You
yeah,
can, with enough energy, you can create new wave shapes, and that would then
yeah.
create.
With enough energy, you could pull a proton and antiproton out, but you
Yeah.
can't pull out just an electron. That's the other point of the medium is you can't just pull. You have to pull them out in pairs. So when they don't create electrons ever, they create electrons and positrons, and then maybe they reannihilate,
Yes,
right? So,
that's a
right?
good, exactly, clue to modeling charge, because whatever, like there's a lot of different charge models, and any model of charge needs to explain that. Like when you can't just create a plus charge. You always create a plus and a minus charge, right? You can't
Yeah,
just have a plus spin.
exactly,
Well, the spin,
exactly.
no, the
Yeah, yeah,
momentum has to be conserved, but the charge especially has to be conserved. You can never create just a
yeah,
plus charge. So any
exactly.
model that models
Yeah,
charge as whatever. If it's just a normal wave, it's
Yeah.
not going to work because if there's a way to create just a plus charge, it's not going to work. You have to have a model that it guarantees you cannot
Mhm.
plate three plus charges and no minus charge, right? So yeah.
Yeah. No, and
That's
I
important to consider. Yeah. So
very, very
mhm.
important. Yeah. So anyway, so I think, it's just an idea. Like I said, if there is a medium, it would kind of self-organize like this, in my opinion, that it would be like if you could zoom into it, like each dot would be an electron-positron pair, and if you could zoom into it, you would see a dot. I don't know, something, maybe, potentially. That's, makes sense that you would, if there is a medium that is ponderable, that we can ponder, that you can model exactly the way you're modeling. You're modeling everything perfectly as if there is a medium that has, like locations and, stiffness between the locations, whatever you want to call them. So, and we know that Bose-Einstein condenses can support transverse waves. So there is an elastic component to this kind of a medium.
Mhm.
And so that's my reasoning for a ponderable medium, which we don't really need. I don't think you don't need it. You don't need it. You can model it perfectly fine without understanding what it is or care, worrying about too much about what it is.
Yeah,
And
I definitely want to find out, but I don't think, hope maybe in my lifetime, I doubt it, but hopefully one day we'll figure it out. I don't know.
yeah,
Yeah, when
yeah,
I talk about these things, I want to usually take the fewest assumptions. So all I'm willing to say is
exactly. Yeah,
elastic,
yeah,
whether it's the underlying structure, there's many different possibilities. And I don't think there's experiments that could prove one way or another. Like you could have many similar models, right? You wouldn't know for sure.
yeah,
Like as long it has to be consistent, of course. Any model has to be consistent, right, through the
exactly.
whole thing.
Right.
And I think it's important to come up with many different models
Yeah,
because we don't
for
know which
sure.
one is right. We don't know,
Exactly.
right?
Yeah,
Yeah,
let's
yeah.
try them all. Let's try them all on and see which one fits.
Yeah,
Right.
right. Yeah.
So my biggest challenge with this idea is like, yeah, the BECs are two-dimensional. How does this work in three dimensions? So that's what I have to
Yeah,
figure.
and also each dot here is really a little vortex, right? So
Yeah.
if you're saying this is a electron-positron pair, they shouldn't have a remaining circulation anymore, right? Because one is turning left, the other to right, and when you add them up, they should have no remaining circulation, right?
Unless there's a tiny separation, unless they don't completely annihilate. If there's a
But why would
tiny,
they not annihilate? Like if you have
yeah,
two, if they're really close,
yeah.
and then why would they stay
Well,
apart?
okay, so
You
yeah,
know?
I think annihilation maybe is the wrong word. If we use destructive interference, then we get a better idea that it's still there. Like when you have destructive interference, nothing is destroyed. It's like it's the words, I think it's the words we use that, cause the problem. If an electron and a positron are waves, as we're suggesting, and that when they come together, they annihilate,
Mhm.
like they have experienced destructive interference is what I wanted to say.
It's
Then
just like the wave and the anti-wave, right? When you add them up,
yeah,
it goes to zero.
but the wave is not
It's just
gone,
transformed. The wave
right?
is transformed into
Yeah,
another wave, right? So you
exactly. And when
have,
you have constructive interference, you get like something that you can see. And when you have destructive interference, you get a node, you get something that's not moving. So it's hard to see, you can't see it. But that doesn't mean that the node doesn't exist. It doesn't disappear. It exists in the wave. So
yeah, I mean, the energy is still there. The energy never goes away,
yeah,
right? So the
yeah,
overall energy is there.
yeah,
Like I was thinking of noise canceling headphones. Like say you have a sound coming in and you have the anti-sound. Well, that sound is definitely gone. It's
yeah.
replaced. Like if you have air moving this way, that's the one particular sound, and
There's
the noise
right.
canceling headphone, it generates the opposite
Yeah,
wave. So
you're right.
that's
The
that. Then
sound is gone because
the
your
air
ears don't
molecules,
hear
they
anything.
stand still, and of course in the process you generate these vibrational thing. So the energy
Yeah,
is there, it's just transformed into heat, for instance, but the actual sound is gone. Like if we would call this sound an electron and this sound is the
I
opposite sound,
see. Then they're gone. They're gone as the
the
entities.
label we
They're
can no longer
they're
say the
You're
tone,
right.
the A
They
sharp.
are
The A sharp
gone
is
as
gone.
the entities. You're right. 100% right. That is true. Yeah.
But the energy is not gone. Like the energy is now in heat. Oh, my ear warmed up a little bit, or who knows, right? So, yeah, I mean,
Yes.
so I'm at that. I think that's my main
Yep.
challenge
Yeah,
is
so
these
it's
labels we
getting the
use,
terms straight, saying things
you
correctly.
know. Yeah,
And
yeah.
I think that's really important to me to say things correctly. So yeah, I guess the electrons and the positrons do annihilate because they are no longer electrons and positrons anymore because all of their ponderable energy was
It has
dumped
been
out.
transformed to something else, right? It's still
Yeah,
there. Like the energy is always there. You can always, in a way,
yeah,
pull it back out by refocusing the energy in some way, and
yeah,
you have the light beams, like yeah,
yeah,
some way. Yeah, yeah, you can get it back in a quote in a sense, and then in
yeah,
this way, when you create this wave shape, you can again create the electron positron pair. But I
right.
wouldn't follow, like you couldn't follow the label anymore. Like you couldn't
Yeah,
follow it.
no, yeah,
Like the
it's
A
just
sharp
like,
sound is gone. It's no longer there. Like
yeah,
I couldn't say where did it go? It didn't go.
yeah.
It's just transformed.
Exactly. And
Mm,
same with like the sodium chloride analogy. When sodium and chloride come together and form salt, it's no longer sodium. Like the properties of sodium, the properties of chloride are gone. And now you have something completely
mm,
different that, a medium that's, you have a medium, you have a solid, whereas before you had a gas. And, it's different than what it was when before they came together and formed the
mm.
crystal. So I just find that interesting. It's fun to think about stuff like that.
Oh yeah, it's great to have, people should be creative and think about because I'm sure there's a lot if we should also allow people to be creative and not just always dismiss everything right away
Yeah,
because maybe even if it's not perfect, right? Maybe the new idea comes out of that, right? Oh, a
exactly.
new concept. Oh yeah, now you
Yeah.
have another idea because a lot of debates I've had led to new ideas simply because
Mhm.
of debating. Like someone telling me
Yeah.
this is wrong, you're stupid, whatever. And I'm like thinking it's trying to explain, oh, now I know, whatever. So
Yeah.
so it's
Oh, for
important to
sure. Yeah.
yeah, yeah,
I
yeah.
agree. Cool.
Cool. Yeah, that's great. So
So
next
that's
time, if it's okay with you, we can dive into general relativity, if that's
okay.
okay. If you want to do
Yeah.
that, or you can I can also
Well,
skip
well, let's
it.
just go
But
in the order you did them before,
yeah,
unless you
yeah.
can
Then
think of any reason to do it differently.
no, I think
Yeah.
the order makes sense, just because I know general relativity sounds difficult, but it's actually in a way the easiest thing because it maps directly to an elastic medium. It's
Okay.
once you understand like how it could, like what Newton was saying, that it's basically refraction. I know people think how could that be, but it's once you see it, it's kind of
Yeah.
trivial, I think.
Yeah.
Um, you
It's
know,
I 100% agree. It's a refraction. And there were some, there are analogies out there that model that general relativity as refraction. So it's not, it's not sort of out of the realm. It's just not as popular. It's not a popular way to talk
well,
about
it
general.
requires this medium, and people don't
Yeah.
like the idea of,
It
they say, oh, it's
exactly.
abstract, it's all geometry, but geometry doesn't do anything.
Yep.
It just bothers me. Like we are saying, general relativity is actually affecting Earth, how it moves, but Earth is real, and something that's abstract cannot influence something that's real. You need something real to influence something real. That's just basic philosophy, right?
Yeah.
So there must be some real component to it. Otherwise,
Yep.
how could you say math influences? Math describes and geometry describes, but you can't have math do something in real life, right? It's just a
Exactly.
description. So
Yeah.
you need some mechanism. And I hope people are more open and actually realize that, yeah, you do need a mechanism. You can't
Yeah.
just, otherwise, you're not going to get any further. So, yeah.
Exactly. There's nothing wrong with I haven't been able to find any flaws in your logic, and I've watched, all of your talks with James, and so each time I'm like, yep,
Yeah,
yep.
you let me
Good.
know.
Yep. Good.
I've thought
So,
about this a lot. So, I might miss some details here and there, but I think overall it seems very consistent. Even
yeah.
I don't know how far your, even electromagnetism comes out. So, which is pretty, that was the hardest
Have
one.
you done anything recently with James, or like have you done Maxwell yet? You haven't done
It's coming out like in May is the last one.
okay. Okay.
Like he wants to release it every 2 or 3 weeks. So it's all online. It's all there. It's just not
Oh,
released.
he's yeah, probably just editing and stuff like that, or just timing it
No, it's
better.
done. It's there. It's just not released. So I think if you ask him, maybe he will give it to you. But
Oh, okay. Because I'm sort of sitting on the edge of my seat waiting for your Maxwell.
I can, if you like, I can share it. But yeah, yeah, yeah.
Yeah. Oh, yeah. I'll just wait for the rest of the world, I guess.
We can meet them. We can
Sure.
do. Maybe we'll catch up. We can do the
Yeah.
next one in a week or something, and then.
I'll definitely I'll go through that the talk with James and
No, you
come
don't
up
have
with
to. I can just do it
maybe
with you. I can just do it with you, and then I get your
Yeah.
fresh look, for
Yeah. No, I just like, like with this one, I'm glad I went through it because then I could show you m my line of thinking,
Yeah,
right?
let me know also if
Because,
next topic, right?
yeah,
Next one would be
yeah.
general relativity. If you have any thing you want to share or
Mhm. Yeah,
discuss, and also criticism is fine. We need debates, right? So if you feel like, hey, wait a minute, didn't you just say that's totally fine, right?
right.
So
Yeah, for sure.
mm,
Okay.
okay.